Hello there guys, and welcome back to another epic inexorable maths video. Very exciting video today, a video that I've been wanting to make for actually quite a while. This is the proof that there are infinitely many prime numbers. There does not exist a final prime number. There are infinitely many of them, and we can actually prove that. You might think it's quite difficult to prove that, because the problem with prime numbers is that there is no formula or kind of way to know what the pattern is for generating prime numbers. They seem to be kind of random. So there's no way of saying, you know, a prime number is described by like this formula. You know, a prime number appears every, you know, whatever. There's just not a formula for this to happen. So we need something else. The way we're going to do this is by contradiction. So let's just dive straight into it. The first step, because it's a contradiction, is to assume the opposite, the contrapositive of what you are trying to prove. So our assumption is that there exists a final prime number. There are finitely many. So there are finitely many prime numbers. There exists finitely many prime numbers. Of course, if there are finitely many prime numbers, there is a last prime number, and it means that you can count them. Now, there might be a million of them, there might be a billion or a trillion of them. We don't know, but we're saying that we think that eventually you're going to run out. There's going to be a last one. So, if there are finitely many prime numbers, we can list them all out. So, prime numbers. This is them. So the first prime number is going to be P1. Obviously, we know the first prime number is the number 2. But like, I'm just going to call it P1, P2, P3, P4, etc. All the way up to the last one, which I shall call Pn, because I actually don't know what the last prime number is. Again, spoiler alert, there isn't a last prime number, but let's say that I think that there is one. I don't know what it is, though, and I'm going to call it Pn. That's the very last prime number, the nth prime number. Okay, that's true. Fine, we're assuming it is. The next step is we're going to consider a new number, which is all of the prime numbers multiplied together, and then add 1 to that. So I'm going to call this number capital N, and it's going to be equal to P1 multiplied by P2, multiplied by P3, multiplied by P4, all the way up to Pn. So it's every single prime number multiplied together and then add 1. Now, this is very clever, because every prime number multiplied together and added, and if you add 1, something you'll see in a second, really cool happens. So, if there's two situations right now, n can either be a prime number or not a prime number. There's the only two things it can be. It can't be anything else. N is a prime number or it's not a prime number. This number here is clearly a whole number, so it can't be a fraction or a decimal, anything like that. It's either prime or it's not prime. So not prime is composite. It's prime or it's composite. Okay, well, if n is a prime number, then we are done, because that's a contradiction already. If n is a prime number, we can clearly see that this number here is bigger than Pn, which we've said is the biggest prime number, because it's a bunch of other numbers, all of which are bigger than 1, timesing together, and then timesing by Pn, and then adding 1. Of course it's bigger than Pn. So we can say, if n is prime, we've already done the contradiction. So this essentially, if n is prime, then it must already be a contradiction of our statement, which is that Pn is the largest prime number. This number is bigger than Pn. Okay, so that means that n must not be prime. N must be composite. Okay, if n is composite, and this is the thing about composite numbers, all of them, can be written as a product of prime factors. You know, you do your factor tree, you do your prime factorization, you know, write the number, you know, whatever, the number 50 as a product of prime factors, etc., etc. You can always write any composite number like that as a product of prime factors. Here's the thing though. The number n, which is p1 times p2 times p3, all the way up to pn and then plus 1, here's the thing. It cannot be divisible by any of those prime numbers. None of them. Why? Because you've added 1 to it. And we know, this is the clever bit, we know that it is divisible by all of them if the 1 isn't there. If you get rid of the 1, then n is clearly divisible by all of the prime numbers, every single one of them. But it can no longer, because we've added the 1, that's why we've added 1, because we added 1, it's not divisible by any of them. And I've actually made a video on this, I'll link it in the description. It's the proof that 2 consecutive integers are co-prime. They share no prime factors. I've already proved that. So I'll leave the video in the description. But you can imagine it, right? The number 50 and the number 51 do not share any prime factors. They can't, because they're consecutive. Their difference is 1. The number p1 times p2 times p3 times p4 all the way up to pn is divisible by every prime number, meaning that the same thing plus 1 must be divisible by none of them. And here's the thing. If it's not divisible by p1, p2, p3, p4, all the way up to pn, if it's not divisible by any of them, and it's definitely a composite number, it must be divisible by some prime number bigger than pn. Right? That's like the thing that we're looking for. Because it's not divisible by any of those ones. It must be divisible by a prime number at least one, and it's none of those. It must be divisible by a value that is larger than pn. And if it's not, then it's a prime number already. In and of itself, n is already a prime number. Which means that if n is not prime, if it's composite, it must have prime factors larger than pn. And you can see if it has prime factors larger than pn, then there exists a prime number larger than pn, which is great because we've proven again that there is no, we've made a contradiction essentially, and therefore you can say therefore contradiction either way. And our original statement is what we were actually trying to prove is true, and that is that there must be infinitely many prime numbers. I love this proof. It's really cool, in my opinion. Okay, so essentially, again, what we did was we said there is a biggest prime number. There is a Pn that's the biggest one. Consider the number P1 times etc. all the way up to Pn, add 1 to it. That new number, capital N, is either prime or not prime. If it is prime, it's already bigger than Pn. So there you go, that's a contradiction. There's a prime number bigger than Pn. If it's not prime, it must have a prime factor that is larger than Pn, because it does not have prime factors between P1 and Pn, because the number n minus 1, if you ignore the plus 1 on the right hand side there, that value is divisible by every prime number. So adding 1 to it means that it cannot be divisible by any of them, because no 2 consecutive whole numbers share any prime factors. That's the thing that we've just really, it's really important that we've got to. And therefore, we've made a contradiction because either way, regardless of whether n is prime or not prime, it implies that there is a prime number that is bigger than Pn. That's a contradiction. There must be infinitely many prime numbers. That's essentially what it is. So, thank you guys so much for watching. Highly appreciate it. And I'll see you in the next video.